4차 산업혁명 기획 10주 1차 시강의를 시작하겠습니다. 챕터 12 신경기술입니다. 신경기술이란 인간의 뇌에 대한 깊은 통찰력을 제공하는 다양한 기술을 망라합니다. 이를 통해 우리는 정보를 추출하고 감각을 확대하며 행동을 변화시키고 세계와 소통할 수 있게 됩니다. 관련 동영상을 보시겠습니다.
Our nervous system is how we communicate with the world. It allows us to taste, see, hear, smell, and touch. Neural interfaces are devices that interact with our nervous system. They can be placed on the inside or outside of the brain or body and can restore or even change what we're able to do. Early neural interfaces, such as cochlear implants and devices to treat hearing loss, first emerged in the 1960s.
Daddy loves you. Daddy loves you. Daddy.
Yes, here.
Can you hear Daddy?
Deep brain stimulation to treat tremors in Parkinson's disease was first approved in the US in 1997. And more recently, experimental treatments have emerged which aim to allow people with paralysis to walk again.
They could even take a few steps over ground, hands-free. For me, seeing this recovery was amazing.
With increased investment and advances in neuroscience and computing, the technology is being miniaturized and becoming more powerful. In the future, neural interfaces could replace some pharmaceutical treatments, meaning that your prescription could be for a neural interface rather than a drug. You may be able to buy neural interfaces to train your brain to improve your concentration or your memory, and they may allow you to perform better or sleep easier. However, the most extraordinary potential uses of neural interfaces concern how humans interact with technology. These include typing using just our thoughts, the truly remote control of robotics, allowing surgery to be performed from anywhere on the planet, and games played using only the mind that are able to adapt and respond to players' mood and mental state. In the future, it may even be possible to use this technology to communicate sensory experiences. You could send a loved one a neural postcard when on holiday. But the use of neural interfaces also raises some critical ethical questions. Neural data, gathered from the brain and body, may be considered more private than data collected from smartphones and other devices. This neural data could be harvested for information about someone's emotions or moods. And using neural interfaces could provide people with abilities that exceed the majority of the population. If only accessible for some, they may lead to a more divided society. Humans have always innovated by using our brains to create new technologies. With neural interfaces, we're now turning that process inside out, using new technologies to transform our brains. These technologies might challenge the very essence of what it is to be human. Working out how, and even if we want to use them, requires an open and inclusive debate, involving many voices and all sectors of society.
신경과학은 병원과 연구실로부터 서서히 벗어나 우리 일상의 일부가 되고 있습니다. 관련 동영상을 보시겠습니다.
Imagine moving a mechanical arm by just thinking about it, or playing a video game using only your mind. Yes! Although it may seem like science fiction, scientists and engineers have been developing this technology for decades. It's called brain-computer interface, or BCI.
The field of brain-computer interfaces relies on the ability of the brain to be able to generate certain types of responses that can then be harnessed by computers, to be able to be interpreted by computers.
Dr. Rajesh Rao is a neuroengineer and director of the Center for Sensory Motor Neural Engineering at the University of Washington and is funded by the National Science Foundation. He is developing safe, non-invasive devices that can connect to the brain to accomplish things like controlling a prosthetic arm or sending commands to a computer.
Looking at the development of this whole field of brain-computer interfaces is to think of it in terms of studying how the brain controls the body.
Whether it's telling the legs to jump in the air or activating glands to produce sweat, the body's actions and functions are controlled by neurons. They communicate information to and from the brain and the rest of the nervous system using chemical and electrical signals.
And so they're sending these electrical pulses to each other and eventually to the muscles that are then controlling my body.
Much like how the brain controls muscles, researchers can use new technologies to tap into these signals to control machines.
The understanding of how the brain controls movement led to the development of devices and algorithms that can be implemented on a computer that recognize these patterns in the activity of brain cells and then correspondingly move an artificial device.
To demonstrate how this technology works, Rao and his team of students use a BCI that allows them to study nonverbal communication. First, the student is fitted with an electroencephalogram, or EEG cap, which is a series of electrodes placed on the scalp to record brain signals.
We need to get ground reference now. Okay. It's at 48.
When a question appears on the monitor, the student answers yes or no by looking at one of the flashing lights, which are blinking at different frequencies. When the subject's eyes focus on one of the response lights, the frequency of that specific light is picked up by the visual cortex in the brain and measured by the EEG cap. 12 hertz represents a yes frequency, while a no is at a frequency of 13 hertz.
Now you can see a peak here right around 12 hertz because no is for 12 hertz.
The computer interprets this signal and moves the cursor in the direction of the response. Using an EEG cap isn't the only way to measure brain activity. Some BCIs use a method called electrocorticography. It also records brain activity, but unlike the EEG cap, it is surgically placed directly on the surface of the brain, providing a clearer signal and more precise information.
For example, they can imagine moving their hand, and we use a computer to extract the patterns that correspond to imagined movement of the hand, compared to, for example, not imagining and just resting.
From there, the computer can distinguish the two types of brain activity: imagining movement and not imagining movement, then use that information to enable hand control by mental activity.
Given the right kinds of information and the right kinds of devices that are useful for the animal or for the human, the brain can start to adapt.
With practice, the brain can learn to do something it's never done before, like control a prosthetic it's not familiar with. But the key is to understand how these neural networks communicate between the brain and the body.
So if you're able to understand the brain better, then you're also able to build better brain-computer interfaces, because then they can use those signals that are responsible for different kinds of movements.
As Rao continues to collaborate with engineers, neuroscientists, and neurosurgeons to develop more BCI devices, he is working toward a future where the brain and technology come together seamlessly.
신경기술은 4차 산업혁명에서 완전히 새로운 가치체계를 만들 가능성이 있습니다. 동시에 중대한 위험과 거버넌스에 대한 우려 역시 낳고 있습니다. 신경기술은 무엇이며 왜 중요한가에 대해서 말씀드리겠습니다. 신경기술은 우리의 의식과 생각을 더욱 잘 조절할 수 있게 해주며 뇌의 다양한 활동을 이해하는 데 도움을 줍니다. 여기에는 새로운 화학물질을 이용해 우리의 생각을 세밀하게 해독하는 것과 뇌의 오류를 바로잡거나 개선하는 것도 의미합니다. 신경기술을 통해 우리는 세상과 소통하는 새로운 방식을 찾고 우리의 감각을 확장하는 기회를 얻습니다. 관련 동영상을 보시겠습니다.
So the first thing is to decide what neurons you're going to decode, which ones you're going to interact with. We actually jump from the brain specifically into motor cortex, and we think about the brain and motor cortex as giving us, here's this picture of a homunculus, a plan of how the brain connects into the body. What you'll notice there is that your hands and your mouth sort of dominate the output of your brain. Those are the most densely innervated parts of your body. Your hand is actually the most densely innervated part of your body. And that's where we collect our neural signals. This is where your skill resides, and this is where your adaptation, your online, real-time, fast adaptation is expressed. And we do that by decoding the activity of individual neurons as they innervate your hands. Using an array of sensors and a technology called surface electromyography, or surface EMG, we're able to actually take a complex signal and deconvolve it. In this case, I'm going to talk about something called myocontrol, and we'll come to that again towards the end. And under myocontrol, we're actually just trying to understand what each of the 14 muscles in the arm are doing. When you're moving, when you're doing natural things that you do today, including the kind of unnatural things you do when, say, you're typing or you're moving a mouse or a joystick. And in this scenario, we actually just deconvolve the signal out into individual channels that map out to muscles. And once we have an online map of what your muscles are doing, we're effectively aware of everything you're doing with the machine today. If we can decode this accurately, then there's no reason for you to have a keyboard or to have a mouse, because I have the information from the nervous system itself that would have otherwise been expressed through those devices. So a little abstract, but I'll show it to you in some videos in a moment. But from here, we do something that's much more exotic. From myocontrol, myo meaning muscle, we jump into neurocontrol. And this is pretty exciting. And one of the first places in the world you'll ever see this. The brain has upper motor neurons up in cortex, and those synapse down onto lower motor neurons that exist in your spinal cord. Those in turn send long axons, the largest cells in your entire body, long axons down and contact muscle. And they release neurotransmitter onto the muscle, and they turn individual fibers in the muscle on and off. And what you'll notice here are 3 clusters of fibers, the dark blue ones, the pinkish ones, and the red ones. Those are called a motor unit, and a motor unit has a one-to-one correspondence with a motor neuron, such that when a motor neuron fires in the spinal cord, that final output signal of your brain, you get a direct response, what's called an action potential, in muscle. And if we can dig inside of that EMG signal, we can decode the actual neural signal and decode these action potentials. With action potentials, we have the zeros and ones of the nervous system. There is no information more reduced than that. And from there, we're off to the races.
복잡한 인간의 뇌는 매우 흥미로운 영역입니다. 두개골은 약 1.4kg의 세포를 품고 있으며 800억 개 이상의 신경들이 100조 가지가 넘는 방식으로 연결되어 있습니다. 수천 년 동안 의식과 경험의 주된 원천이 뇌라는 사실을 입증하기 오래전부터 화학물질의 변화를 통해서 자신들의 행동에 영향을 주는 법을 알았습니다. 음주, 코카 흡식기, 흡연, 환각버섯 섭취 등은 종교적 이유나 유흥 목적으로 인간이 어떻게 자신들의 사고 과정 또는 행동에 영향을 주었는지 보여주는 좋은 예입니다. 이러한 물질들의 사용은 논란이 되어 왔습니다. 심지어 커피와 같은 양호한 물질들도 등장한 초기에는 수차례 금지되곤 했습니다. 두개골 절개, 철학, 심리학, 뇌스캔까지 인류는 뇌를 이해하기 위해 다양한 방법을 시도해 왔습니다. 하지만 이제 신기술은 뇌 속의 화학 및 전자 신호를 측정, 분석, 독해, 시각화해 줍니다. 이는 경제적 기회를 제공하고 의료혁명을 가능하게 하는 한편 방대한 범위의 윤리, 사회적 문제 역시 야기할 것입니다. 신경기술은 다음 3가지 측면에서 중요합니다. 첫째, 뇌를 읽고 영향을 주는 능력은 가치 창출을 위한 새로운 산업과 체계를 이끌 것이며 이는 깊은 사회, 정치, 경제적 함의를 갖습니다. 생명과학의 경우와 마찬가지로 결점을 개선하고 기능을 향상시키는 능력은 신경기술과 관련된 서비스를 거래할 능력을 가진 부유층에게 매우 큰 이익을 가져다 줄 것입니다. 이와 동시에 인간 내면 깊숙한 곳까지 읽어내고 영향을 끼칠 수 있는 힘은 알고리즘과 데이터 수집이 일상화된 세상에서 심각한 골칫거리입니다. 둘째로, 신경기술은 새로운 형태의 인지 컴퓨팅과 머신러닝 알고리즘의 발전을 통해 다른 4차 산업혁명 분야에 혁신을 유발합니다. 신경기술을 이용해 뇌의 비밀을 밝혀낼수록 뇌와 상호작용하거나 뇌의 기능을 복제하는 기술을 발전시킵니다. 셋째로, 뇌는 사람을 사람답게 만드는 데 있어 핵심적인 역할을 합니다. 뇌는 우리가 세상을 인지하고 이해하고 배우고 상상하고 꿈꾸도록 해주며 사람과 사람 간의 교류를 가능하게 합니다. 뇌에 보다 정교하게 영향을 줄 수 있다면 우리의 지각, 경험, 심지어 현실의 의미까지 바꿔놓을지도 모릅니다. 뇌과학은 인간이라는 시스템의 운영에 영향을 줌으로써 인간의 자연적 진화를 초월할 수 있도록 합니다. 관련 동영상을 보시겠습니다.
So just what is a BMI? So you start with hopefully a brain and a machine, but the machine is just a stand-in for the outside world. It could be another brain, it could be software, it could be a robotic arm, but you want to receive energy from that world and impart through the senses like vision and audition and impart energy back into the world through things like motor control. And that language that they use to communicate, it's important to understand what that language is. And that language is information. And we, as far as we know, everything that we care about is found in the statistics of spikes. So that's what we focus on.
Nearly 100 billion cells called neurons. Neurons come in many complex shapes, but generally they have a dendritic arbor, a cell body called a soma, and an axon. The neurons of your brain connect to form a large network through axon-dendrite junctions called synapses. At these connection points, neurons communicate with each other using chemical signals called neurotransmitters. Neurotransmitters are released from the end of an axon in response to an electrical spike called an action potential. When a cell receives enough of the right kind of neurotransmitter input, a chain reaction is triggered that causes an action potential to fire, and the neuron to in turn relay messages to its own downstream synapses. Action potentials produce an electric field that spreads from the neuron and can be detected by placing electrodes nearby, allowing recording of the information represented by a neuron.
And so why does that mean that you have to be inside the brain? So you want spikes. Well, people have studied if you take a neuron and you put an electrode on that specific neuron, and then you place an extracellular electrode nearby, and then you measure how far away from a neuron can you be, and it turns out that the answer is about 60 microns. The long academic heritage of research here. The cochlear implant has reached millions of patients since the 50s, and so the question is, why not use one of those devices? And in the Utah array case, the rigid sharp metal electrodes produce a fairly strong immune response. And this doesn't end up hurting the patient, but it does mean that you lose the ability to record single spikes over some period of time. Whatever we built, we wanted it to be completely wireless. We didn't want any connectors or wires coming through the skin. It had to be something that would last for a long period of time, not something that you'd have to take out at 2, 3, or 4 years in. It had to have practical bandwidth. So we talk about high bandwidth or ultra high bandwidth. Like, what matters is that for the task that you're after, there's practical bandwidth that allows you to effectively do that thing, whether that's cursor control or typing or robotic arm or maybe in the future vision. And it has to be usable at home. It can't be something that you go into a clinic at the hospital for 2 hours a week and under tight supervision of technicians plug you into the amplifiers and turn it on. It has to be something that you can live with. And so 2.5 years ago, we were nowhere close to any of that. This is a photo of some of the prototypes that we've gone through over that time. So we started on the far left. That's an entirely passive board that has 64 electrodes on it and connects to connectors that go to big external amplifiers. And then we added integrated electronics with our first custom chip. That's also 64 channels. And then there was a big leap to the device that Elon showed a photo of earlier. That has 3,072 electrodes in a fully implantable package with just a USB-C port coming out. And then we took a step back in channel count because remember we have to optimize safety, longevity, and bandwidth all together. And so in order to optimize some of those other things, we moved to an easier to manufacture system that has 15, 36 channels and a USB-C port. And those last two are the focus of the paper that we released today. And so we've learned a lot from these. We've recorded a lot of data through these. Like these are actually used every day at Neuralink to record neural data and work with it. And they taught us a lot about the architecture that we think was the basis for our first human product that we're calling N1. And the central component of that is the N1 sensor. It's a little hermetic package. When it's fully assembled, this is missing an outer mold. It's into an 8 millimeter diameter 4 millimeter tall cylinder. And each of these has 1024 electrodes, and we can stim and record through every one of those channels. Exploding it, opening it up a little bit, you can see there's the thin film, which has the threads that Elon talked about, which is the wisp going off to the side. There's a hermetic substrate, and then that gets welded later to a package that goes over top, and that's mated to our custom electronics. And we'll go into more detail. We'll have the technical leaders that work on each of these talk about these in more detail over the rest of this presentation. So yeah, I mean, this is just not to belabor the point. I know that Elon really hammered this in, but these things are very, very small. They're not. You can't manipulate these. This is one photo. This is not two photos joined together, and you really can't manipulate these with your hand. That part at the top is just a backing material that's surgical packaging. They're peeled off. The threads are peeled off that one at a time by the robot to place into the brain, and we had to build a surgical robot. And the first impetus for this is just you have to place these threads. You can't manipulate these threads. You need a robot. And then that grew into understanding where the blood vessels are and imaging into the tissue, and the surface of the brain moves because you're breathing and you have a heartbeat. And there's lots of complexity of dealing with this incredibly high entropy substrate. And it's not all offloaded to the robot. The robot's under the supervision of a human neurosurgeon who lays out where the threads are placed. But it would not be, the surgery is not possible without the robot. And so the N1 implant, we can place, as Elon mentioned, many of these, possibly up to 10. In one hemisphere, for our first patients, we're looking at four sensors, 3 in motor areas and 1 in a somatosensory area, which are connected via very small wires tunneled under the scalp to an inductive coil behind the ear. And that connects wirelessly through the skin to a wearable device that we call the Link, which contains a Bluetooth radio and a battery. And this is, importantly, the only battery and radio in the implant. So if you take this off, the implant shuts off. And if there's software upgrades or security issues, it's much easier to upgrade the firmware on the pod than it is to try and change the implant. It'll be controlled through an iPhone app. You won't have to go to a doctor's office and have them have an exotic programmer to configure it. And the first thing that you'll have to do is learn to use it. Like, imagine if you've never had arms, and then suddenly you have an arm, and you have to pick up a glass on the table. It's like not a cognitive task. You just how do you can't think your way through that. And so it's kind of a trippy experience at the beginning, where like patients, at first it just kind of wanders around, and then they figure out how to break the symmetry, and they learn how to control it. And that's like it's a long process. It's like learning to touch, type, or play piano. And so for the first product, we're really focusing on 3 distinct types of control. The first is giving patients the ability to control their mobile device, because we heard from over and over again from patient groups that if you have to have a caretaker around to press buttons for you, what's the point? You might as well have them do the thing. You have to get self-sufficient using the devices on your own. And then redirect the output from your phone to a keyboard or a mouse on a normal computer. It'll just show up as a Bluetooth mouse or a Bluetooth keyboard, like any keyboard or mouse that you can use on any computer. And as Elon mentioned, this is a forward-looking statement. There's a whole FDA process we have to go through. We haven't done that yet. This is like, these are aspirations. But we are working as hard as we can towards our first in-human clinical study next year. And again, these are plans, but the primary indication for that will be complete paralysis by upper cervical spinal cord injury. And we're expecting that those patients will get 4 1024 channel sensors, 1 each in primary motor cortex, supplementary motor area, and dorsal premotor cortex, which are 2 motor planning areas, and closed loop feedback into primary somatosensory cortex, which is like when you type or walk or pick up a pen, those aren't visually guided movements. Your body has all these senses of where it is in space and pressure and temperature and lots of other feedback. And we think for really high fluent control, you have to provide that back to the brain for the synthetic effectors also. And of course, fully wireless and able to use it at home. We think that there's a huge difference between something that you get to use 2 hours a week at the hospital versus something that you're living with every day and your brain is adapting to as much as the device is adapting to your brain. And so to bring up the other colleagues, this team is like, I'm incredibly lucky to get to work with this team. We're going to go into a little bit more detail on, I think that decoupling implantation from the electrodes is incredibly important. The reason that you have these issues where things like these tungsten microwires get rejected is they're stiff and they're stiff and sharp and they tear the brain, and they have to be because they have to get into the brain. And so if you can decouple the process of getting it into the brain from what is left there, where it can be much softer and have material properties like the brain and maybe be coded in things that help the brain recognize it as itself, that's really important. And then the thin film polymer leads, the threads themselves, are really cool material science, and we'll go into more detail on that. And then we'll also talk more about the chips, and then a little bit more on just the neuroscience of how information is represented in firing statistics in your brain.